Hello, this is a screencast for solving problems with the gas law equations that we've been using in class lately. I thought this would be a handy thing to have before entering into the exam in about 2 weeks. So what we're going to start with is the different pressure units. What we see here is all of these are related or equal to one another, meaning 1 atmosphere is equal to 101.3 kilopascals. 760 millimeters of mercury is equal to 14.7 psi. So we set up a domino or factor labeling equation to solve for the unit that we want. So I'm going to do 2 examples. I've given you answers to a second set of problems, and you can try to solve for these particular answers. So we're first going to start with this one here. So I'm going to write down what I'm given. I want to convert this to ATMs. Well, I know that 1 ATM is equal to 101.3 kilopascals. So what I'm able to do is say the kilopascal units cancel out, and I end up dividing 303.9 kilopascals by 101.3 kilopascals, and I should come up with 3 ATM. We'll try another one. We'll look at 190 millimeters of mercury. We want to find out PSI. The unit that I want is going to go on top, so I got 14.7 PSI. That is equal to 760 millimeters of mercury. I can cancel out my units there. If you like, you can put this or set this over 1. So we would multiply the numbers on top and then divide by the number on the bottom. And when we do so, we come up with 0.37 PSI. So what I'd like you to do is try the conversion factor of 29.4 psi to ATM and convert 1.5 ATM to kilopascals. So I'm going to move down the screen and start looking at some Boyles law problems. So in Boyles law, we have the equation of P1 is equal to V1 and P2 is equal to V2. This is an inverse relationship, so as pressure goes up, volume is going to go down. We can set them equal because anytime that we change one of the first 2 variables, we automatically get a change in the second set of variables. So if I was going to set this up, what I would first try to do is indicate where my variables are. So this is V1, a gas that occupies 12.3 liters at a pressure of 40 millimeters of mercury. So that's my P1. What is the volume? I'm going to circle that because that's what we're going to solve for. And I'm looking at my P2. So my equation would be set up as 12.3 liters multiplied by 40.0 millimeters of mercury. And that is equal to V2 times 60 millimeters of mercury. If I want to get V2 by itself, we should know that we can divide this side by 60.0 millimeters of mercury, canceling out those units. So now I have V2 down here, and that's equal to 12.3 liters multiplied by 40.0 millimeters of mercury divided by 60 millimeters of mercury. I know that I can cancel that out. So if I multiply the top and then divide by the bottom, I come up with an answer of 8.2 liters. I'm going to try another one. This time we're going to solve for P2. So here's my V1, 6.0 liters of helium gas at a pressure of that's my P1. The gas is pumped into a balloon that only holds V2, and we're trying to find P2. So I plug in my numbers. 6.0 liters multiplied by the pressure, that's my P1 pressure, is equal to my V2 in this case is 1 liter, and I multiply that by P2. I want to isolate P2 by itself, so I can divide out by 1.0 liters. That cancels that. P2 comes down here. And we should multiply the top and divide by the bottom. I cancel out my units, and this answer comes out to 15,000 kPa. All right, so those are examples for Boyle's law. We've had a lot of practice of that in class. This is just a friendly reminder on how to use that equation. I'm going to move down into Charles' law. In Charles' law, we have the variables of volume and temperature. It's a direct relationship, so as temperature increases, volume will directly increase. I'm going to work this problem in two different ways to show you how to manipulate this equation a little bit differently, and it might help you in the future. So, first thing I can start out with is identifying my T1 temperature, and here's my V1. What temperature? So I'm looking for T2. Should it be lowered to bring the volume to 300 milliliters? So there's my V2. If I use the standard equation, what I'm going to end up doing is having 500 mil on top over 27 degrees Celsius really gets converted to Kelvin equals Celsius temperature plus 273. So that temperature ends up being 300 Kelvin is equal to my V2 of 300 mils over my T2. How I would solve this is I would multiply each side by T2, and it looks like I ran out of room here, so hold on a moment, folks. So we look at 500 mils over 300 K is equal to 300 mils over T2. Multiply each side by T2. And that cancels out and that cancels out, and I'm left with 300 mils on that side. I want to get rid of these numbers, so I isolate T2 by itself. So now I can cancel that out, and I can cancel that, and I'm left with T2 is equal to 300 mils multiplied by 300 K over 500 milliliters. I can cancel these units out. I end up multiplying 300 times 300 K divided by 500, and I'll come up with a T2 value of 180 K. What we can do is rearrange this equation a little bit and write it as, if we do some cross multiplication, we can quickly do V1 times T2 is equal to V2 times T1, and it might set up the equation a little bit faster for some of you. So my volume 1 temperature is 500 mils, so I can go 500 mils, and that's being multiplied by T2 if we're following this equation. And then that's equal to V2 and T1. My V2 volume is 300 mils, and my T1 temperature is 300 K. This sort of gets you into the equation faster without all this additional algebra. Might be useful for some of you. I divide out 500 mils like I did on the top, and I end up with a T2 equal to 180 K. So I just wanted to present this method to some of you because I think the Boyles law question or equation is easier for some of you to work. So if you understand a little bit of that cross multiplication presented in math classes, you can apply that concept to your Charles law equation. Write it like this, and then I think it just looks a little bit easier or simpler to solve. All right. I have a practice problem available for you, so you can try either method. Always remember to convert to Kelvin temperature. I provided you the answer here. Following the Charles law, we can look at Montaigne's law, which is a relationship between pressure and temperature. It's also a direct relationship, meaning as I increase my temperature, my pressure will increase, or if I decrease my temperature, my pressure would decrease. This formula is the same as the Charles law formula with the exception of the P is the new variable. I gave you answers to these problems. See if you can solve them. We're going to go on to the combined gas law. Let me take some of this, get rid of that. So combined gas law, we put Boyles law together with Charles and Montaigne's law and looking at the behavior of gases in more of a realistic situation. Very similar setup. What we can end up doing is identifying our variables. So we have a P1, we have a V1. If the temperature where the balloon is released, this would be our T1. What will happen to the volume? So we're looking at essentially V2 with our T2 temperature. Okay, so I'm going to rewrite this. We have 105 ATM, which is multiplied by 5.0 liters, which is equal to here's my P2, 0.65 ATM at, I'm looking for V2. This is over a temperature of 258 Kelvin, and this is over a temperature of 293 Kelvin. That's my T1, and that's my T2 temperature. What I can end up doing is dividing this side by 258 K over 0.65 ATM. I do the same thing on this side, so I have 2.58 K over 0.65 ATM. I can cancel out, well, this cancels out this, and this cancels out this, so you're left with V2. Cancel out my units there. I cancel out my Kelvin there. I multiply the top and I multiply the bottom, and then I divide them, and I should come out with an answer of 1.7 liters. So I gave you a combined gas law problem, and I shared the answer with you. So I would like you to try this problem using this technique, or you can rewrite this equation as P1 V1 multiplied by T2 is equal to P2 V2 T1. Might be a faster way to set it up and solve it. We should always remember that Kelvin is degrees Celsius plus 273. We always need to convert to Kelvin. So I'm going to go on to our last one, which is the ideal gas law. Second to last one, I think. No, this is our last one. The ideal gas law. In the ideal gas law, I'm going to use this variable since we've never used it in any of the practice problems in class, and it's really not that much more challenging than using the one that you did in class. Here's our equation. So what we can do is just identify some of our variables. So here's a P, here's a V, here's a T, and it looks like we're searching for moles. So 303.9 kPa multiplied by 31.0 liters is equal to N multiplied by 8.3145 liters kPa divided by moles of K times our temperature, which should come out to 360 K. I'm using kPa, or this standard, because my initial pressure was in kPa. If this was in atmospheres, then I would use this constant. So I want to solve for N, so I can divide this side by 83145 liters kPa over moles of K. Everything cancels out over here, and I'm left with N is equal to whatever operation I ran over here, I transfer that same operation over here. Now we can just begin to cancel out some units, if that helps. So that goes, and liters is gone, and Kelvin is gone, and we're left with the only available unit as moles. If you run out this equation, you'll end up with that N is equal to 3.14 moles of the gas in this equation. So I'm going to run another equation right here, trying to solve for, I believe, pressure, and then I'll give you an opportunity to try an example on your own. So I look at this and I have my N, here's my volume, here's my temperature, what is pressure, standard temperature, I'm just going to use ATM. So P times 60 liters is equal to 3.00 moles multiplied by the standard, or R value, for this when we're using atmospheric pressure units. And I have a temperature of 400 Kelvin. I divide this side by 60 liters, so that cancels that out, and I have P by itself, so that's equal to, so we multiply the top together and then we divide by the bottom, and your answer should come out to 1.64 ATM. I'm going to go back up to this equation here. It looks like the answer has been erased somehow. So N equals 3.15 moles. Okay. Here's the last ideal gas law problem given to you. I gave you the answers. This is in sig figs. So you should try to work this problem and see if you come up with the answer. If you have any problems or questions about what I've done in this screencast, bring your questions to class, and hopefully this is a good resource for you while you're working through understanding the gas laws. Thanks for your time. See you in class. Bye.